I'll
This
do
one,
that.
okay. It's on.
Wait, this goes around my neck?
So around the ears here.
Really?
I believe so.
So, this works. So it's a pleasure to be here. And so let me start with a motivating slide due to my colleague Dave Patterson from a talk he gave last semester to give you some motivation for why we want to worry about low precision. So this is the energy on a log scale of a whole bunch of different operations, including communication, moving data, doing multiplies, and doing adds. And since it's on a log scale, get this to work. So it takes 45,000 times as much energy to do a single 8-bit integer add as it costs to go off to DRAM and get your data. And so that's a good reason to avoid communication. But even if you're just talking about energy on a single chip, it takes 50 times as much energy to do a 32-bit floating point add as an 8-bit add, and 30 times as much energy to do a 32-bit multiply as an 8-bit multiply. So whether you're worried about the battery in your cell phone dying, or the $1 million per megawatt per year it costs to run your data center, or how long your drone can stay aloft, or climate change, we should try to reduce energy, which means both reducing communication and reducing precision. It's some 7 nanometer technology proprietary to Google, I think, which is where Dave is now. Yeah. Okay, so here's the outline of my 3-part talk. I'm going to start by giving you a summary of the P3109 standard for floating point. And there's a public version open for comment now, and I invite you to download it and send in your comments. And I have 5 pages of references at the end of this talk that you can all look it up on later. So the second part of the talk will be grading the BLAS. And so the question is, what accuracy guarantees should all the folks who are building BLAS implementations using tensor cores and other things, what should they promise the vendor? And as the people who are in charge of the BLAS standard, how can we verify the promises made for proprietary code based on our public tests? How can we keep people from gaming it? And I should say an early version has been adopted by NVIDIA. They actually do an extra n-cubed work to make sure they get the highest possible grade in our grading scale. And so what they do is they do some computations to make sure the exponent range is narrow enough that they can get away with their emulation code, and otherwise they fall back to FP64. And then the third part of my 2-hour talk, that's how long I get, right? So, is to talk about exception handling. And we've been working on this for quite a while to say what behavior should libraries guarantee when you have infinities and nands and things like that, and how can we verify these promises. And what's relevant here is if you're doing emulation and you're not doing floating point, what do exceptions even mean? And I should say we have found bugs dating back to Isomax in the BLAS 1 before nands and infinities were invented. So I think we know how to fix that one, but there's a lot of tools that we've developed to try to discover new bugs before we actually release them, or 30 years after we released them. Okay, so let's go on to the summary of the 3109 floating point standard. And so why is this standard committee exist? Because 754 is still around, and we're meeting at the same time. In fact, both committees meet every 2 weeks and alternating weeks because many of us are in both committees. So just as in the days before IEEE 754, many companies are inventing their own standards for low precision arithmetic, and they would like to have a common way to do it. And so they came, they were supportive of creating a new standards committee. And so here are the 3 widely used standards currently out in industry: OCP, AGQ, and TSL. TSL is Tesla only. And there are some references to them where you can look up more details. And so the question is there some common format and set of operations that all these companies can agree on? So this committee was convened in 2023 with lots of representatives from all these companies to try to find a common design. And as you can imagine, it takes a few years to get an agreement on all these sorts of things. And so it's nice that we have an interim report out there, which is actually, we think, close to convergence. And so it's the same motivation as for 754. It's nice to have a common design that will give you portability and reuse of not just the hardware, but software and training data. And there are lots of stakeholders in this business. Okay, so I'm going to try to summarize the whole design on 5 slides. So there's a bunch of parameters here. And so I would actually say it's more of a menu than a standard. There are actually hundreds of different options if you look at the entire possible design space. So first you get to choose the storage width, how many bits per word. And I'm pleased to say a few weeks ago we had a vote. And we decided not to include 2-bit floating point arithmetic. It has to be at least 3 bits. But we do have an appendix in the draft standard with all the possible formats that you could have in 2 bits and why they're all ridiculous. Okay, we could go up to 16, but in principle, less than 16 is what's of most interest. So then, once you pick the number of bits per word, you get to pick the number of significand bits. And it can go all the way down to 1. And that's basically a logarithmic representation. Then you have to decide if it's signed or unsigned. And if it's unsigned, you get an extra manticipit. And then you have to decide if you have infinities or not. Is the domain finite or extended? So all of these are legitimate standards. And so here's the notation. And these colored letters refer to up here. So you could have binary, 4 bits, P1, 1 bit of precision, unsigned, and finite numbers only. And so all those different combinations are in the standards. On top of that, we have a lot of different rounding modes. I'll give you a list of those. We also have multiple saturation modes, how to handle overflows. And then there's a bunch of operations. Most of them will look very familiar from 754, but there are also some new ones. Okay, so what do these 2 choices of these last 2 decisions make? Is it signed or unsigned? Is it extended or finite? So if you decide that you're going to represent signed numbers and it's extended, that means you have positive and negative finite numbers, 1, 0, no negative 0, 1 nan only, and plus or minus infinity. If it's finite, you again get the positive and negative finites, 1, 0, and 1 nan only. Now if it's unsigned, you only get positive finite numbers, 1, 0, 1 nan, and plus infinity only. And if it's unsigned and finite, positive finites, 1, 0, and 1 nan. So one consequence of just choosing to always have exactly 1, 0 and 1 nan is that 1 divided by 0 is now nan. Because otherwise, if you take the reciprocal of minus infinity, you'd get plus infinity. And that seems like a bad idea. We also have subnormals all the time because the experience of all the ML folks is that gradients behave much better if you can represent all those tiny numbers. But there's been some recent email, there's so much email in these committees, about having possibly supernormals. That means replacing the subnormal numbers with numbers that are larger than what used to be the overflow threshold, and you just get powers of 2 that go up past that. And because some people want that to avoid infinities, even though you don't have a lot of precision at those very large numbers. So where does that nan live? It replaces minus 0 in the representation. And there are no exceptions because if you have 1,000 processors all running at the same time, it's very hard to decide how to throw an exception. This is also a debate in 754 that I'll get to later. There are only rules for how you deal with plus, minus infinity and nans. Very similar to 754 with some differences like this. Okay, what are the rounding modes? So these are mostly similar to 754. Round to nearest, ties to even, that's required. That's what most people use in 754. But there's also round ties to away, round positive, round negative, round towards 0. Those are all in 754. Oops. There's a new one, which is also going to be added to 754 as a recommended rounding mode, to odd. So what does that mean is, if the computed result is an exact floating point number, that's what you get. But if it's not exact, if it's in between 2 adjacent floating point numbers, you round to the odd floating point number, even if it's farther away. And so why is that? There's been a bunch of discussion, but I'd say the only recommendation that has remained is it avoids double rounding. So double rounding is when you compute in higher precision and then round to lower, you may get a different answer. But if you round to higher precision in this funny 2-odd mode, and then round down to whatever direction you like, you get the same answer. And so people would like to have that. It turns out there's 3 different kinds of stochastic rounding. And I'm going to refer to this paper for the details. But the goal in stochastic rounding is to round up or down proportional to the distance that you are from the other end. So that would require, to implement that precisely, would require an infinite number of bits. So obviously you can't do that. So there are all these different approximations out there where you generate a finite number of bits to decide whether you round up or down. But there's so many different approximations that the committee didn't want to decide between them, and that's why they're all there. We also do not specify the number of random bits. We leave that entirely up to the vendor because there are just so many choices, and random bit generation can be very expensive or not. Yeah, so anyway, all that is in there. So so that's rounding modes. There's also the question about how to handle overflow, and there are 3 choices there. You could do it as an IEEE 754, you overflow to infinity. Or you could saturate, which means you clamp to the largest finite number. But if one of the inputs is actually an exact infinity, you propagate it as appropriate. And the other one is saturate finite, which is you clamp all values to the largest finite number. And again, all these are in there because people have found it useful depending on their experience with their particular machine learning application. So here's a very partial list of all the operations. Many of them are very familiar ones that are also in 754, but I'll point out some differences. There's fuse, multiply, add, but there's also fused add, where you compute the sum of 3 numbers with 1 rounding error. And so people decided they wanted that. There's also all the usual elementary functions, which should look familiar, but there's a new one called soft plus. And this is basically a continuous approximation of ReLU, which people want for machine learning applications. And please go see the draft standard for a complete list. So people do not want to promise to get the right answer. So it's also possible to say, I'm only going to get the answer within kappa floating point numbers. So cap equals 0 means all of these are going to be correctly rounded. But if you say cap equals 1, you give yourself some freedom. I can be at most 1 floating point number farther away from the correctly rounded value. Or you can say cap equals 2, or you can say whatever kappa you want. It gets useless at some point, but we're giving the vendors that freedom to make those decisions. So, I mean, if x is an 8-bit number, you should just do table lookup. And you can get it exact, but they want to give the vendors the freedom in order to do this. There's no specification made about what approximation you use. You just need to specify, is it correctly rounded? Can I be at most 1 floating point number farther away, or 2, or whatever? It's a requirement of the documentation. And the last page there's also block operations. You can have a whole array of numbers along with a scale factor that they all satisfy. So this is meant to represent all these numbers, but in shorter form than would be required to have all extra exponent bits. And so what can you do with these? You can add blocks, you can do sum reductions, you can compute dot products, and so forth. And so I'll let you read the standard for the other ones. And there's a bunch of other operations, no surprise. 754 is very long. This is very long too. You can ask, what format do I have? What are the rounding properties? You can convert between formats, all the standard stuff we're used to having. Okay, so to summarize, there's a very large design space. Oops. And there are many more formats than 754. And vendors are not expected to implement all of them. But what they have to do is document which ones they actually do. So if you're building a special purpose chip for a particular set of inference problems, you probably know exactly which small subset you want, and that's what you should document. And so this is very much a compromise between the desire to have custom formats and portability, but that's the way sort of life is. So you may remember that back in the 1940s, von Neumann was against floating point, and his point of view was that if you're smart enough to write a program, you should be smart enough to scale all your data. And so you shouldn't use floating point. And of course, that argument did not win. Floating point won. But I think we're back now in the same situation, that it's the experts who know how to scale their data that are writing all of this code, and they want the decision making of all exactly what format to choose. So maybe we'll go someday and do that differently, but that's where we are right now. So there's also been a lot of work on formalizing the specifications and building tools for validation. In fact, somebody just reported a bug in the standard because they built a lean proving system for the format, and they found a bug in the documentation, not in actually the thing we've released, just sort of how it's described in English. And so if you want to know what the differences are between this standard and all of these other ones, OCP, AGQ, and TSL, if you look at Appendix C of the proposed standard, it has a list of all the differences. And so just to give you some examples, some of them have -0, which we do not. Some of them have multiple nans, and some of them do not have negative infinity. So it's just sort of an interesting collection. They're all different from one another. So you may be wondering, what about 754? That's been meeting again regularly, and it's required by IEEE to meet every 10 years to see if it needs to change. And the only, well, maybe not the only, one of the significant changes is we're probably going to add a new round to odd as a recommended rounding mode for the same reason I gave before. And there's been a lot of email about exception handling with parallelism. Because, what does it mean if you have, 1,000 processors, and all going in parallel, and one of them throws an exception? What does that mean? How should it propagate? Do you want the actual mantissa of the NAND to propagate in some way forward? How should that happen? And let's just say there's more email than I've had time to read. Okay, so we have built a simulator for doing all of these and more. It's all public domain on GitHub. And it's a C++ interface where you can instantiate any combination of all these types that you want. And it has a whole bunch of interfaces that make it easy to use. So for example, it has a PyTorch interface. So you can tell PyTorch to automatically use any one of these different things in different parts of it. It has shortcuts available if you want to say, I want to use one of these 3109 types, or OCP or TSL, they're all built in. And it can store all of your custom floating point numbers either as short bit strings or as native hardware floating point. And we've tried to optimize it to make it go fast. It tries to use the native floating point hardware on your platform, like if you're on a GPU, and then round it back so that it tries to go as fast as possible. We support microscaling. We have interfaces also to mixed precision BLAs that you can use and sort of tune the precision inside of it. And we also have some custom exception handling, because 3109 NANDs are different from 754 NANDs. So anyway, and there's a pointer to the GitHub reference there. Okay, so that's the end of the first part of my talk. I don't know if I'm on target time or not. We'll see. So now I'm going to move on to this. Are there any questions before I move on to grading the BLAs? Okay, many new BLAs implementations, as you all know, using low precision accelerators, and in particular using integer arithmetic accelerators, and sometimes even using Strawson-like algorithms. One of my former postdocs has a startup in that area. And so the question is, what can or should a BLAS implementation guarantee in terms of the precision they offer? And given that guarantee, how does it impact higher level algorithms as an LAPACK? So what we have is a grading proposal, which I'll go into detail shortly. And so where you get either an A or a B or a C, depending on, those are the only passing grades, depending on what kind of precision you guarantee. And so what we need to do is design tests that cannot be gamed, because our tests are going to be public, but BLAS source code is proprietary. We want to make sure that our tests are ungameable, and I'll show you what progress we've made there. So initially we thought we could design these tests to reverse engineer the underlying algorithm. But we finally gave up on that because it's just too hard to foresee whatever a large language model may imagine or hallucinate tomorrow. And under some assumptions, which for example is the algorithm is not chosen randomly at each call, that's just a joke, we believe our proposed tests are reliable, that we can actually tell you very guaranteed way whether you deserve an A, B, or a C. So let's go on to what the grades are. So here's the lowest passing grade that's satisfied by Strawson's algorithm. So I want to multiply A times B, and the difference in norm between the floating point result of A times B and the true result is bounded by some modest function of the dimension times machine epsilon times the norm of A and the norm of B. So this bound's been around for a very long time. Lots of error analyses of Strawson-like algorithms have been done, and it's been used for lots of different backward error analysis. So that's the lowest passing grade. Here is what classical BLAS does. It gets an A. It says that the error in the ijth entry of the product is the classical dot product error analysis. So you take the dot product of the ith row of A, the jth column of B, with the absolute values, so the sum of absolute values times some function of n times epsilon. And there's a theorem that goes back to 1975 that says that you cannot attain this lower bound, this upper bound, unless you do n-cubed operations. It cannot be attained by any Strawson-like algorithm. And so the other nice property that we're going to use for our tests for this is it's invariant under diagonal scaling. So if I take A and scale its rows, B and scale its columns, and scale the columns of A and the rows of B by this common factor that cancels out, that just all filters through here. So that's a nice property that that error bound has. And so I have an A, I have a C, what comes in between? So here's the new error bound. And it says that, again, it's going to be component-wise error bound, but now it's going to be proportional to the norm of the ith row of A and the jth column of B. That's what comes in between. And that's what's going to be satisfiable by emulation and by Strawson if you scale carefully. So this is in between bounds 1 and 2, and it's invariant under diagonal scaling of the rows of A or the columns of B, but it's not invariant under this common scaling by D3. Okay, so ideally, any BLAS implementation should publish whichever one of these bounds it satisfies. And obviously, you can do better than this. You can get an A+ if you get each entry of A times B to high relative accuracy, but we're going to use that maybe for generate our test cases, but we're not, it's expensive and we're not going to test for it. Okay, so let me give you some examples of our tests and the testing results. So here is a sort of a natural thing to do, but it's gameable. But I'm just going to put it up here for, to give a starting point. So I take A and B, fill them up with random numbers, and then I set a few randomly chosen rows of A to 0 and columns of B to 0. And then those zeros should propagate through into the rows and columns of A times B. And any n-cubed algorithm will do that, but Strawson will not. Because the only way you get those exact zeros if you get exact floating point cancellation at the very last step. And that's not likely that all those zeros are going to appear with high probability. But this is easy to game, and in fact, if you implement Strawson, you should do this. You should start by scaling all your rows of A to have norm 1, if you can, all the columns of B to have norm 1, if you can, then do the multiply, and then undo the scaling. That makes the error bound better. But if you do that, you'll detect the 0 rows of A and the 0 columns of B, and then you can fix it at the end. Oops. Okay, so this next test, you sort of saw my trick there. We originally thought this was not gameable. And so what we're going to do is we're going to pick some random rows of A and make them randomly sparse, about 50%. Then, for each one of those, we'll pick a random column of B and make it complementarily sparse. So when you compute the dot product, you get a sum of zeros. And any n-cubed algorithm will get a 0 there. But Strawson will almost certainly not. And so this is really nice because we can also thought we could reverse engineer the base case for Strawson. We keep making the dimensions smaller until we do get all zeros there, because that's when Strawson would switch from Strawson algorithm to an n-cubed algorithm. And so our conjecture was this works for Strawson-like algorithms in general. But I was giving this talk at the Simons Institute last semester, and somebody in the audience came up with a way to game it. So can anybody think of the way to game this one? Okay, here's the trick. You take your output, you look for tiny entries. If they're tiny enough, you just set them to 0. And so you could, that will make it indistinguishable, perhaps, Strawson from any other algorithm. Okay, so let me show you some test results of using this test. And so these are for randomly this is the test 1A, the one that's gameable, the 64 by 64 matrix. And these are SPI plots. So the whites are zeros, the greens are positive, and the reds are negative. And so this is the result of running netlib-laws, so it gets you the sparsity pattern you expect. Here are 3 different flavors of an emulation algorithm, a paper by Ozaki and others in the room from 2024 and so we just downloaded their code and we modified it in several ways. We'll get to that. Here's Strawson, just sort of basic Strawson, and you can see it failed. But here we did the trick where we either scaled the rows and discovered 0 rows and propagated them, so it got the right 0 pattern. And here's where we also set tiny entries to 0, but that's irrelevant for this. Okay. And since that picture is a little bit hard to understand, I'm just going to give you pictures where I show you black dots where it got the wrong answer. So here we can quickly detect that these 2 flavors of Strawson got the wrong answer, but all these other ones, gameability was possible. Okay, here was the result of test 1B. So we got this other case of Strawson, and it failed, but the zeroing out continued to do the gaming for us. Okay, so here is the not gameable one, but we've given up on reverse engineering Strawson. We're just going to say, do you get an A or not? And so we're going to strengthen that test, the last test, so only an n-cubed algorithm using conventional floating point can possibly pass it. And so what we're going to do is take those examples from the previous test case, on the previous slide, and I'll pick pick a few pairs of rows, whose rows of A, columns of B, whose dot product is supposed to be 0, and I'll pick 2 entries and I'll set them to some tiny number, like the square root of underflow. In that case, I shouldn't get a 0 as the exact answer. I should get x squared, right around underflow. And then I'll set all the other entries, non-zero entries in that row and column to be about the square root of overflow. And so both Strawson and n-cubed with emulation should get x squared wrong, and diagonal scaling should not help, because of the way I've built it, all the rows and columns have the same norm, so scaling won't help. So what happens now, here's the results of that test, and everybody fails except for netlib. So we've successfully detected all of these other ones having failure modes, independent of the kind of scaling and trickery they put in. So here is another example. More testing is more reliable. So this one, also has, uses a different approach. We basically let each row of A be a constant vector x, all of whose entries are random numbers between 1 and 2. Then we scale each column by some number, and then we do the same thing for B. Each column is just x, and its rows are scaled by D3 inverse, so A times B, each entry is just the dot product of x times x transpose, the sum of random numbers between 1 and 2. Should be perfectly accurate. But Strawson, or n-cubed, with emulation will be inaccurate. But this is easy to game, because we can undo this scaling by D3 just by choosing our own scale factor to make each column of x and each row of y have the same norm. So that's actually a good thing to do if you want to make Strawson more accurate anyway. So here is our second test, which we thought was not gameable. I'll take each A and B from this one and circularly shift the rows and columns. And so when I'm done with that, all the rows and columns of A will have the same norm, so diagonal scaling is pointless. But now, only the diagonal entries of A times B should be accurate. They're going to be tiny numbers and compared to the rest of the matrix, and they should be accurate only when using n-cubed with standard floating point. And so we thought that was not gameable, and then we figured out a way to game it. And what we can do is just recompute the diagonal entries only using standard floating point. So if you're running Strawson or one of these or emulation, you just do an extra n squared work and you're fine. Okay, so yeah, we have to think of these adversaries at these companies who are trying to cheat on our tests. And so here's the not gameable way to do it. I'm just going to randomly permute the rows of A and the columns of B, and so there's tiny numbers that you would need to recompute or who knows where. And it's obviously not worth going to look for them and computing them all accurately. But you're welcome to suggest more games. Okay, so now that I know that you get an A or not, how do I decide between getting a B or a C? So here is the idea. I'll just set each entry of my matrix to be random numbers between 1 and 2, so A times B is always accurate. And then I'll just do some diagonal scaling by some wildly scaled numbers going from the square root of underflow to the square root of overflow. And I'll do the same thing for B, and that should be just as accurate as doing it this way. And if you do that, that says you get a B. Otherwise, you get a C. You're doing Strawson. And so let me show you some results of this test. And so this is these are plots of the error. Let's suppose I was going to compute f of n. So it's the error divided by epsilon times the true result. And that should always be, order n. And so you can see that, and this is on a log scale. So, it gets up to between 1 and 10 as the factor of f of n, and all the error bounds are satisfied by the Ozaki scheme or netlib or Strawson if I do all of that scaling. But the error bound goes up to 10 to the 250th for Strawson if you don't do that. So this is a clear detector that you do not deserve a B. You only get a C. And there's one more possible test for Strawson that is sort of amusing. I'll take any of the previously suggested A's and B's and choose some random permutations. And then what I'll do is I'll compare this product with that product. In other words, I do the permutations before or after the actual multiply. And obviously, if you're doing an n-cubed algorithm, that should be irrelevant. Get the same answer. But if you're doing Strawson, you're taking sums of different submatrices, and you'll take different sums, and the chances are 0 that you'll get bitwise identical answers. So we thought this was a good idea, and then we found two flaws. The first one is that floating point summation is not necessarily reproducible. We've heard about that. And so, you might get slightly different answers here, but maybe it doesn't, they're close enough that we can still use this. And the second flaw, is there an echo here? And this is a question for the emulation folks in the audience. This is why it's good to have these meetings. I'm assuming that the scale factors for emulation for A only depend on the rows, and the scale factors for the emulation done with B only depend on the columns. So that if I permute them, I get the same scale factors. But, I'm hearing an echo here. Let me turn off my sound. But if your scale factor depends on a block, a subblock of the data, then permuting, doing this permutation may give me different scale factors, and therefore I would not get bitwise identical answers. So this is a question for folks in the audience: what submatrices you use to determine your scale factors. Okay, so now, what about that factor f of n? What do we expect? Because we should give you a grade on how bad f of n is. Obviously, if it's 10 to the 250th, you failed. But what else should it be? So in the non-Strawson case, let's just think about, so we're just thinking about dot products here. It could be anywhere from log n to n, depending on whether you do your summations with a binary tree or n. And in the average case, if you're rounding up and down half the time, it could be anywhere from n to square root of n. And so what we might want to do is grade this separately and tell the user, this is how your n is growing, to give them a hint. And it's also possible, alas, that we may need to give different grades for different problem sizes. Because what if a vendor uses classical floating point for small matrices and then switches to Strawson for large matrices? They may satisfy different error bounds for different problem sizes. And so that's something we may want to detect as well. Okay, so that's all about GEM. How does this extend to the rest of linear algebra? So here's TRSM. And so there's also an A, B, and C grade. C and A have appeared in the literature before. So the question is, how big is the residual when you solved Tx equals B? And if the error is proportional to the norm of T times the norm of X, you get a C. If it looks like the matrix multiply, you get an A. And if it depends on the row and column norms, you get a B. And so we have yet to do any confirmation work on publicly available code for this as to who satisfies what. And finally, how does this scale up to a higher level routine, like solving AX equal B? What different error bounds can you satisfy here? So I'm going to assume that I'm just going to take the LAPACK code, and I'm going to take all the BLAS3 implementations and use a version that either gets an A or a B or a C for all of them. But I'm going to assume that BLAS1 and BLAS2 go unchanged. So this is also a question for folks in the audience. Is anybody bothering to use emulation for BLAS1 or BLAS2? I know you're not using Strawson, but I don't know if you're using emulation for BLAS1 and BLAS2. So here are the different bounds you can get depending on which accuracy you get. So let me take my SPD matrix and write it as a product of diagonal times H times diagonal, where H has ones down the diagonal. So there's a classic theorem, goes back to 1969, that says that this choice of the diagonal matrix to put ones on the diagonal of H nearly minimizes the condition number of H. And so it's possible that the condition number could be much, much smaller than A if the diagonal entries of A, vary greatly in magnitude. Okay, so what I want to do is tell you what the error bounds are for both the computed solution and for the residual and the Kleski factor. So let's suppose you just get a C, you use Strawson, then what's been known for a long time is the error is bounded by epsilon times the norm of A in the residual, that's good. And the error in the solution is epsilon times the condition number. So classic stuff we teach all our students. What if you get an A? So this result was sort of hinted at by Wilkinson in 1968, but he only stated it informally. And then I later wrote a tech report in 1989, but I didn't bother publishing it because Wilkinson already said it. And finally, Nick Hyam put it in his textbook in 2002. So you can read the proof there. So the residual in the error it looks like matrix multiply. The dot product of the ith row of L and the jth column of L transpose is the bound on E. But I get a much, much better forward error bound. So this is the error with the scale factor, and it only depends on the condition number of H, which can be arbitrarily smaller than the condition number of A. So that's bound 2. And then finally, what if you only have a B? You get that same error bound. And here's the bound on the residual. It's this diagonal II times diagonal JJ, but this error bound for the forward error is the same. So, and there's similar results for LU and QR and stuff like that. Won't go into the details. So here's future work and open questions. So we're doing grading now, but there's still a lot of work to do for GEM. We still have to devise tests for the other BLAS3, all those examples of test 1, test 2, test 3. We have to make them up for TRSM and so forth. Do we need to test the possibility of using different algorithms or different arithmetic depending on problem sizes? So this is a question for vendors. It's a question for the folks in the audience who are building these libraries. So far, I've assumed that the output precision, my epsilon and my error bound is the same epsilon as is used to represent the output matrix C. But we could be using higher precision internally, mixed precision. And I haven't worked out any of those error bounds yet for all these different algorithms. And so the question is, should we worry about that too? Should we assume that somebody is going to use emulation with higher internal precision than the final output answer? And we have to extend all this. Oops, sorry. And what about BLAS1 and BLAS2? At the moment, I'm assuming that nobody is using emulation for BLAS1 or BLAS2, but I could be wrong. So please let us know. And then, leading into the last part of my talk, is what do we do about infs and nands? So what does emulation do if there's an infinity in the input? Or if there's an overflow in the middle of the computation? How is that propagated to the output? And so we have, this is the last part of the talk now, a whole bunch of rules we've come up with for the classical BLAS and classical linear algebra codes as how you should propagate infs and nands consistently. Yes?
So this result, these error, these grades are the same regardless of matrix structure?
Structure meaning like if it's diagonal?
Well, yeah, structure in terms of there's a lot of sparse matrix.
So obviously, if you have structure in your matrix, the simplest example being maybe the zero matrix, multiplying by that is very accurate. But I'm just trying to give a bound that's true for arbitrary inputs, worst case. But if you want to say your grade for your gem, if your matrix has this extra property, well, that's an enormous design space that we haven't thought about.
Yeah, and sometimes random and zero are the easy cases.
Yeah, but all our test cases were, designed specifically to get around that, to say what's the worst case. Yes. So any questions before I move on to exception? Yes. Yes. Well, so as long as f of n is not 10 to the 250th, as long as it's growing modestly with n, we can try to do a bunch of examples for different values of n, and do some and plot all the f of n's versus n, and do some sort of simple fit and say it looks like it's order n, or it looks like it's square root of n. It's not an important part of the grade, but we could do that. Yes. Yes. Right. That's why I was saying, do we need to, somewhere I had the question of, do we need to do this, get a different grade for different problem sizes? So that's certainly part of the potential design space. And so that would be easy to do in the sense that a user or a vendor, could tell our code, our test code, here's the range of n we care about. You don't have to go to n equals 1,000,000. Yes?
I think one thing that would be interesting to do in the class is actually to have the user say, I want a grade of A level, a class of B level, a class of C level. For example, I can see lots of implementation of my code and I just don't care about normal stability.
Right.
So if I just care about normal stability, I just want to say my class.
Right. So in other words, you have blas underscore A, blas underscore B, and blas underscore C. Yes. That's in some sense what I guess NVIDIA did, because they have a branch internally in their code to decide, do they just do emulation or do they fall back to FP64 if necessary? And so that's sort of a flag, which is I want an A, but they could turn that off. Is someone here from NVIDIA to speak to that? I'm not sure what options are exposed to the user. Okay. Okay, exception handling. So this is a summary of a very detailed list of existing bugs and proposed fixes. You're welcome to read our 90-page archive paper, but you don't have to. And we submitted an NSF DOE proposal to correctness, and maybe someday NSF and DOE will wake up again and review our proposal, but we haven't heard back yet. This is all under active discussion in the 754 and 3109 committee meetings. People care about exception handling. And I'm sure many of you have heard the stories about people like to tell to motivate this, airplanes crashing and rockets crashing. My favorite, more recent example was from just a few years ago. There was a Reddit page with a picture of a robotic car that had crashed, so nobody got hurt, during the training run. And at the bottom, there's a little post from the engineer in charge of it who said, oops, a NAN appeared during the training round. Right, so anyway, these things are important. And so the main question for this meeting is, how should emulation deal with exceptions, either on input or internally generated? So let me just sort of tell the story from doing the original BLAS. So here are our rules for being consistent. So the first rule is thou shalt terminate. You should not go into an infinite loop. Now, obviously, that's undecidable in general, but the LAPACK code and the BLAS is even simpler. They don't have such complicated loops that you can't tell. Basically, you should never have a loop that says repeat until the error is less than a tolerance. Because if you have a NAND that propagates, you'll never stop. And so we're very careful never to have a loop like that in LAPACK. So the second rule is that infinities in NANDs should propagate to the output in some way so they're not lost. And they could either appear as a floating point number in the output, or there's a flag reported to the user, so that means the programmer, so that that information is not lost. So Alternatively, they could be explicitly dealt with by the programmer. So we have some loops in LAPACK where we expect infinities, and we've done the error analysis, and they're okay, because we divide by that infinity and it goes away. And so in those cases, you can ignore the infinities. Or there could be some simple, well-documented, user-approved cases where infinities don't matter. So if you call gem and you do 0 times a plus b plus 0 times c, the documentation says we don't care what's in A, B, or C. We just want the output to be all zeros. And we're not going to change that. But that's well documented and everybody wants it. And for LAPACK, we propose some reporting using info and even more if you want. But there are not going to be any changes to the BLAS interfaces. And this is based on a very large number of requests that we've made to our users, and DOE has a whole, workshop, and report on how they want exceptions to be handled. So this is all sort of well documented. We didn't make it up. So here are some of the challenges that we have in order to deal with this, which is that we are writing code that's based on, which we want to be consistent, but it's building on an inconsistent substrate. So a compiler may or may not use fuse, multiply, add. That will, and if depending on whether you do or not, you may or may not get an overflow because of the way rounding is done. Summations can be done in any order, and so it's easy to add 4 numbers. And with this particular choice, depending on the order I add them in, I could get a plus infinity, a minus infinity, a nan, or a 0, right? And we have to deal with that possibility. All those could happen. C and Fortran define complex arithmetic differently. So if you do this particular multiply in Fortran, you get nans. And if you do it in C, you get infinities. And in fact, the C standard provides 30 lines of code in order to implement this. Now, how many compilers actually, by default, implement those 30 lines of code to do a single scalar complex multiply? Well, it depends on the compiler flag you set. And so obviously we have no control over these kinds of things. This is just the life we live with. It turns out that in 754, 2008, min and max were not associative operators. They did not propagate nans in a consistent way. And so we fixed that in the last release in 2019, but programming languages may not have adopted that yet. So their mins and maxes may or may not be associative. And so how are we going to live on this framework and have a consistent definition? It's outside our scope. We have to live with this stuff. And so basically we say if there's an int for an and, we'll propagate it. We're not going to distinguish between the two. Okay, so let me give you this bug that's been there, bug in quotation marks, since before 754 was invented. This is Isomax, one of the simplest BLAS1 codes. It returns the index I of the largest entry in absolute value of an array. And so there's the code, all 3 lines. It's pretty simple code. We'd all write it unless we knew better. And so here's the inconsistency. If you take Isomax of an array of length 3 with 0 nan 2, it tells you 2 is the largest. But if you do nan 0, 2, it tells you the nan is the largest because of the way that if statement is written. So that seems inconsistent. And so what we decided to do is that, we have to decide, should we point to the nan if it exists or the first largest number? That would be okay if nan meant missing data, because some people think of it that way. But we're going to point to the nan, because in numerical code, you shouldn't have missing data. It turns out that Isomax is even worse. So here, you have a finite input and an infinite input, and it tells you the finite input is largest, because of the way it's written inside. And so you can get the wrong answer even with all finite inputs. And so, so we have some code out there that fixes this. But this inconsistent behavior is a standard, as we like to say, because the BLAS is a standard, but we're going to have to change that. That's what standards committees are for. So here's another example of an inconsistency in TRSV, a triangular solve. And so here, T can be upper or lower, and it can be general or unit. So here's some things that can happen. Here's a 2x2 triangular system where the triangular matrix is upper triangular with a nan in the second column. And if you solve it, it tells you the output is 1, 0. It does not propagate the nans. This is the standard BLAS code on NetLib you can download. Now, here's another example where there's a nan, it's a 3x3 problem. And here, the nans do not propagate because TRSV checks for zeros in X, and it does not multiply them. So when it comes down and sees the zeros in X, this value is a 0, it will not propagate it. So that's another way that can happen. And it turns out that if you take this top problem and you take the transpose of this matrix and then ask to please solve the transpose, so you're solving the transpose of the transpose, same linear system, it does propagate the nans because it does not check for zeros in this case. So anyway, this is all silly stuff. It's been there for a long time. And so how do we make it consistent? Again, it depends on what your definition of nan is. If it means some finite number, you just don't know what, then 0 times nan is 0 is okay. But if it means anything, which is what IEEE 754 assumes, then 0 times nan should be nan, and that's what we're going to insist on for consistency. And again, this inconsistent behavior is a standard, and it's potentially much faster. Now, why is that? It's because TRSV checks for trailing zeros in the right-hand side. And if it finds trailing zeros, it'll skip all that work, and it may solve a much smaller triangular system, and that could get the complexity down from n squared to n. But if you don't if you're avoiding multiplying by nans, maybe that's a bad idea. We found lots of similar examples. You can read our report. All of these BLAS routines have examples. So the question is, can we automate the discovery of such bugs? And the answer is yes. And I'm pleased to say this paper won a Best Paper Prize at Arith last year. It uses what's called spoofing. So what it does is it's very hard to come up with an input that will generate a nan or infinity at some point deep inside your code to see what happens. So what this does is spoofing. It does a symbolic execution, and it automatically inserts an infinity or a nan somewhere in your code to see what happens. And it does that at a whole bunch of places inside your code and sees if they propagate or not. And it uses an SMT solver to generate an input that tries to generate them. So it actually does try to come up with an input, but it does spoofing to discover the example in the first place. And so we found a bug in general band matrix vector multiply. And this is actually analogous to SPMV. So let me go on to the sparse case. I'm almost done here. So the sparse BLAS has many similar issues. So, so what does it mean if you're doing a sparse matrix vector multiply and there's an infinity or a nan inside of X, but all of these are 0, right? So what should what should the sparse matrix definition be, right? Because we're not even supposed to bother doing those. It's going to ignore that A times X. Now, so it seems reasonable to say, okay, we'll just, that's what the user expects. You shouldn't multiply a missing, 0 times X. But there are a lot of optimizations which introduce explicit zeros that weren't in the user's input. And that's register blocking. So you take your matrix and you break it up into 2 by 2 blocks, and you put specific explicit zeros in there. And then you use a vector operation to multiply that 2 by 2 or 4 by 4 times a vector. And so you may introduce 0 times nan when they weren't there before. And so the question is, what do we do about that? Should we have a paranoid version, which is very careful never to multiply by a 0 that's not there, as well as a reckless version that's as fast as possible? Reckless will win, but maybe for debugging you want the paranoid version. Yeah, well, a strong 0 is what a sparse matrix is supposed to be. Yeah, so that would be the paranoid version, I guess. Yeah, well, yeah, OSCI's an old project, yes, but yes. Okay. Yes. Right. Right, and the assumption is, are you allowed to say, do you assume all the zeros in your sparse matrix are strong or not? Yes. That's the question. To be decided by yet another BLAS, sparse BLAS standards committee, yes. Okay, so that's the end of my talk. I don't have a list of all the collaborators who are the committee members. There's dozens and dozens of them. Please feel to go look. Here's the collaborators on low float, here's the collaborators in grading the BLAS, and here's the collaborators in exception handling. And I have 5 pages of references where you can go, read all the details if you like. So that's all I had. Thank you very much. Yes.
Thank you for this very interesting talk. So my question relates to the not a number technique. So back in the old days, when IEEE 754 was formed, I read that there was no explicit function to detect NaN. So
It's called ISNAN.
sorry?
Yeah, it's built into the 754 most recent several standards. It's called ISNAN.
Yeah, yeah. And, so back then, the qualification was it is the only element that is not equal to itself. So then, just my question I have to.
Yes.
So
Well, yeah, but can you trust, the question is, can you trust the compiler not to sort of optimize away A does not equal A? It may just decide that's false, so.
another direction.
Okay,
In 2019, IEEE added the total order predicate
yes.
for NaN. So I wanted to hear your opinion on this because it does 2 things.
Mm-hmm.
First thing it says, NaN is the smallest, it always compares as the smallest element,
Mm-hmm.
and is equal to itself. Well, how would you weigh in for last implications of that?
Oh, that's a good question. Yeah, I don't know. So I haven't thought about that particular one. So could we use it to propagate NANs differently than we do now? I don't think it would change our definition of consistency, but it may make it easier to implement. I haven't thought about that. Good question.
So there was this, you were worried about gaining the system by having a higher precision internal representation, even though it's on the outside.
Well, I wouldn't say that's gaming. I'd say that's a feature that you, good, that most people might like.
So that's fine.
Yeah, but should we test for it?
Yeah, so with stochastic rounding, if you wanted to have the version that biases the rounding to the in the direction that you're closer to,
Mhm.
you have to have an ALU that actually is operating at a higher precision than the base precision of the operands you're operating on.
Yes, and so I've had this argument with people that why isn't it cheaper just to keep it in the higher precision instead of doing stochastic rounding at every step?
No, I think you have to do the stochastic, and then you demote it back.
Yeah, the question is, yeah, but it's probably worth, since generating the random numbers and doing the stochastic rounding might be much more expensive than just doing the accumulation if you're doing a dot product in the extra bits and then just rounding at the end. And so that's going to be a hardware optimization question that, the committee's not going to decide.
Yeah, I don't know. It's like if you look at dithering, if you bias in one direction consistently, then the dithering doesn't work.
Yeah,
You have to have a running error.
yes, yes. Yes.
You mentioned the lookup tables for the slow precision. So, I mean, in some sense, you can think of it as a lookup table in hardware, and it's hardwired, but you can just look it up as you get out of the cache. And so I just keep reloading and different lookup tables, so I'm just changing my mind depending on which one of what I'm tuning.
Right, and which is fast? Well, the whole reason to do this is to go fast, and so I'm willing to believe that the vendors will implement a lot of this using hardware implementations and keep the lookup tables only for things like exponentials or whatever that they might find more challenging to actually implement using regular arithmetic if they want to get correctly rounded results.
But I think Bill Donnelly, when he gives the talks for Portability, he says, like, we are pretty much at the stage where we will look stochastically at what numbers we want, where we're going to differ.
So you probably heard the same speech Plenary he gave recently. So another format, which I haven't discussed, that NVIDIA has adopted and patented, is that they, in real time, you can decide to compute a histogram of all your data, and it will compute a custom floating point format for your data. And so it'll have a table where the numbers can be spread apart arbitrarily, more densely, where you have more numbers, packed together in your data set, so you, in your histogram, and spread farther apart where they're rarer. And so multiplication is in the, yeah, and so, and then it will, do whatever arithmetic with a lookup table is required. Every arithmetic operation will be require a lookup table. So the other thing they have, we're not going there here, so yeah, would that be a B minus? I have no idea what grade that would get. So I'm trying to stick, yeah, so once we have such an implementation, I suppose we could, try it. So another example that he spoke about in the talk, that you may know about, is they have a purely exponential format. So it's a sign bit times a base to a power. The base is like 1.1 something, right? So the numbers are, you can choose actually, I think, how close together they are. And so, it has some relative precision, which is, depends on how close the base is to 1, and the numbers are, just powers of that. So multiplication is just cheap. You add the exponents, which are integers. But for addition, they just compute a table of how many times each number appears in the eventual sum to do a dot product. And then they do a lookup table to translate each, b to the, that number time, 100 times that b to the number to a regular floating point number, say. And then they do the actual additions in regular arithmetic. So yes, all of these things are out there. Yeah, because you have to convert it. Yeah, absolutely. And that's why I think it's only implemented, useful to do in a dot product, because you can, amortize the cost of it by if the dot product is very long. Yes. So yes, well, so that's a question of what should we give them a failing grade for. And let's suppose that you have an emulation routine that does a great job in a narrow range of inputs, exponent range, and it just gets the wrong answer if your numbers are too big or too small. In that case, the idea is we would give them a B probably, in that exponent range where they do a good job, and then say, F, in the exponent range beyond that. But if they do, so we have some examples. Yeah, so let me say, in some of our examples, test cases, we deliberately chose it so the numbers were scaled from overflow to underflow. And you'd have to undo that scaling. If you don't undo that scaling to get it into the narrower range of the emulation code, then you'll get the wrong answer. So I'm looking forward to talking to the emulation folks in the audience to see if how much they've worried about this and how they deal with it, and adjust our grading accordingly. So you guys, so yes. Well, actually, there's several people in the audience who've written a paper in the back row about that. So, shall I try to summarize it, or do you want to? So here's the trick, which is you proposed, is we know that in LU with partial pivoting, the worst case is a pivot growth of 2 to the n. So you can engineer that worst case example to make it 2 to the k for any k less than n that you like. And so then what you can do is adjust k to see when LU breaks. And you can sort of detect whether you're doing real blahs or not. I think, was that the proposal you had? Mm-hmm. But without a test necessarily. Okay, just by honor code. Yeah, well, yeah, and we've explicitly decided not to go with honor codes. You have to pass your test. Yeah, closed book and all, so yes. It's up to the organizers.
So another idea that fit basically from the bad guy, quote unquote, AI, right? They use these, for
Mhm.
You do your sparsification, your permutation, adding this precondition, dense preconditioning, that kind of undo things and it spreads the problems all over the place. And I was just wondering if that's something.
So, I mean, does that mean that our tests would give the correct low grades to those implementations? Okay. Okay, I haven't thought about, I don't know the details of the algorithms you're referring to. I look forward to talking about it. Mhm. So I'm happy to, how should I share the slides? I just finished them at 5 this morning, so.
We'll figure out.
Okay, because I'm obviously happy to share. There are a lot of details and references, which I'm very happy to share. Okay, thank you.